Hi, I'm Simon, an anesthesiologist and founder of SCATS Education. I've helped hundreds of students crush their science classes and reach their dream grades. I know what it's like to not understand your professor and feel overwhelmed with this material. That is exactly why I created SCATS Education. Stick with me, and I'll help you achieve your goals like the students I've worked with before you.
All right, so next we're going to talk about the acidity of alcohols. So to talk about that, we have to find what reagents can actually cause alcohols to behave like an acid and deprotonate it. So there are basically two ways to deprotonate an alcohol. One, you can use a strong base called sodium hydride. So if I have this ethanol here and I react it with sodium hydride, which is essentially just a hydrogen with an extra set of lone pairs, that functions as a very good base, not as a good nucleophile, but a very good base. It can simply pick up this H, and you will get this ethoxide ion plus H2 gas. So that's the first way. Second way that you can deprotonate, not as commonly seen, but you can simply react your ethanol with a metal. Which metals? Lithium, sodium, or potassium. And any of these metals will simply cause the alcohol group to simply just get rid of its H and deprotonate. So you can have here's our same old ethoxide ion, but now it's just going to be stabilized by a metal. And you get, again, 1/2 hydrogen gas. Don't worry too much about this byproduct. Just be aware that you can use any of these metals here to deprotonate an alcohol. So now let's talk about what factors influence acidity of alcohols and phenols. So it's going to be a lot of the same factors that you learned earlier in organic chemistry. Let's first start with the first factor, which is going to be resonance. So if I have these two compounds, which compound is going to be more acidic? So very easy to understand. All you have to do is basically deprotonate both of them and see which negative charge is going to be more stable. So if I deprotonate the compound on the left, I get this. With a negative charge. And if I deprotonate the compound on the right, I get this. Well, if you notice, the compound on the right can do resonance. These lone pairs can come down here. This can kick up into a lone pair. And you get this. The same thing can happen. These lone pairs can come down here to form a double bond. This becomes a lone pair, and etc., etc. I won't draw out the next resonance structure, but you can see that the compound on the right has resonance when it gains that negative charge, and therefore that negative charge will be more stable. And if it's going to be more stable, the compound is going to be more likely to want to form that negative charge. Well, how does it form a negative charge? By acting as an acid. So since the negative charge is more stable, this compound will be more acidic than the compound on the left. The next factor that you should already be familiar with is induction. So with induction, it's simply about the surrounding structures next to the negative charge. So remember, the larger the electron cloud for a negative charge, the happier that it will be, the more stable that it will be in making that acid more acidic. So for example, if I have these two compounds, remember, how do we evaluate which one is going to be more acidic? Deprotonate both and see which negative charge is more stable. So if I deprotonate the compound on the left, I get this structure. If I deprotonate the compound on the right, I get this structure. Now, what's the electron cloud of the compound for the negative charge of the compound on the left? Well, it's probably centered around somewhere like right there, just kind of localized to that oxygen atom. But on the right, we have these electronegative groups right here, these chlorines that are very electron withdrawing. And so they're going to stretch out the electron cloud for that negative charge. So it's not just going to be centered around the oxygen, it's going to be kind of stretched out like this. And therefore, that makes this negative charge much more stable. And that makes the compound right here much more acidic. So this compound is much more acidic. Now, while we're on the topic, the reverse can be true. If you have a compound that looks like this, I'm just going to erase the compound on the left for a second here. If I have a compound that looks like this, and instead of electron withdrawing groups, I have electron donating groups like these R groups, or these methyl groups in this case. If I deprotonate this guy, I have this negative charge. Now that the R groups are electron donating, they actually squeeze that electron cloud really, really tight. And so the electron cloud kind of looks like this. It's really, really centered around that oxygen atom. Remember, the bigger is better when it comes to the electron cloud for a negative charge. So that makes it much more unstable, unhappy. And this is not going to be as acidic as the compound that we had here prior. All right, so now I'll put two compounds on the board, and you can use what we just learned to figure out which one is going to be more acidic. This will be compound A. This will be compound B. Take a second to pause the video and think about it. And when you unpause, you'll have the answer. So to figure out which of these compounds are going to be more acidic, we do the same thing as we did before. We're going to deprotonate, and we're going to evaluate which negative charge is more stable. So let's do the same thing for both of these guys. And so now we see that compound A on the left has some resonance. You can bring these electrons down, bring these electrons here. And you form this. And then these electrons can also participate in resonance with this carbonyl group right there. So you can form a lot of resonance with this compound on the left. Versus the compound on the right, these lone pairs do not have any resonance, and there's no other forms of induction, the second factor that we learned, to help influence any acidity. So which compound is more acidic? It would be this one right here because of extra resonance.